Hello, and welcome to 5-Minute Math. Today we are looking at the Algebra 1 concept of writing exponential functions, specifically from real-world situations, and we'll do it in 5 minutes or less. So we have this word problem here about people who own a car and the number increasing about 0.3% each year. We have a starting amount of 133 million, and we want to know what is a function that would work show the total number of cars that is X years since that starting year of 2000. Okay, so let's see what our function is going to look like at the end. So our exponential function, kind of our standard form here, is going to be y equals a times b to the x. So that's what we're looking for, where a is going to be our constant. So in this case, it's going to be, you can call it multiple things. Principal, if we're dealing with money and compound interest, or you can call it a starting amount. Or if we were to graph this, you could call this the y-intercept. So really, that y-intercept is what happens when x equals 0, correct? So we're looking for that starting amount. So in that 0 year, that starting amount, what is the number we're dealing with? And that's that 133 million. Okay, so this b is going to be your growth, or sometimes your decay factor. So how much is it going up? How much is it going down? And so in this case, we've got this increase of 0.3% each year. And then x is typically your unknown. That is, in most cases, going to be your time frame. In these situations, how many years, weeks, months. And that's the exponent, because this growth is not linear, it's not quadratic, it's exponential growth. So that x is going to be your unknown time frame. So how do we put all this together? Well, let's write f of x, since we are writing a function here. Let's start with our principal amount. So that's going to be your 133 million. And then we need our growth or decay factor. In this case, we are growing by 3%. So, or 0.3%, we need to turn that into a decimal, right? So in order to do that, we're going to move the decimal over twice, or divide by 100. It becomes 0.003. Now that's the growth factor. In order to make this function, we need to keep the principal in there, which means we need to add 1. So if we keep 1, we can calculate and keep the original amount in there. If we just use this growth factor right here without the 1, that's just going to get us the percent growth, and then we'd have to add the original back in each time. It's a pain. So we're going to write 1 point, and then there's that 003, and then we're going to take it to the x power, because that's the time frame, and we don't know what that x is. So it's a strange looking exponential function, but that is how we would model that. Let's look at another example. So in this case, we have water flowing out from a tank. We've got our decay rate there of 6.5% per hour, starting amount of 8,500 gallons. We'll write a function that models the amount of water left in the tank after h hours. So let's write our function. F of h equals, remember, a is going to be our principal, starting amount, it's the y-intercept. So when x equals 0, at 0 hour, what do we have? Well, they gave it to us, 8,500. All right, so the only tricky part, if there is going to be one, is finding this growth or decay factor. So it's 6.5%. So we need to do two things. First, we need to change that into a decimal. So that is going to be, move it over twice, or divide by 100. 0.065. Now that's the decay factor. What we need to do is we need to take this away from 1, because we want to keep that starting amount in there. So if we just do the 0.065, that's going to show us how much it goes down, but doesn't keep the original in there. So if we need to subtract this from 1, you're going to get 0.935. That's our actual factor. So we put that in there. 0.935, take it to the h power, and that is how we would write it.